So thank you very much for the introduction, and welcome everyone to my talk on the work that we've been doing to do with implementing a steering platform to do with simulating a magnetic microswarm. So as the contents of the talk, I'm just going to give a brief introduction to microswarms. Obviously, we've just heard a lot about them as well, so I'll keep that brief. And then I'll talk about the maths behind the simulator that I've written, what we've implemented, and then sort of the verification and a bit of a parametric study that we did. So the work that we've been doing is related to microswarm or micro or nanoswarm. This is a large number of particles made up of, this is a swarm made up of a large number of particles that range in size from somewhere in the nanometer scale up to possibly the micrometer scale. For example, in all of this work, I'm considering particles of around 800 nanometers across, and a large collection of them will form a swarm that is a few micrometers across. So why would we want to use these little particles, and what use do they have for medicine? Well, so we can use these particles in conjunction with magnetic fields, for example, for increased uptake of drug delivery. So by either controlling the path these particles will take through the vascular system, we can directly direct them to a certain site to degrade and deliver drugs, or we could just, for example, hold a permanent magnet to a place where we wanted the particles to collect, and this can help to increase the amount of drugs delivered to a certain space, increasing treatment. Slightly differently, we can also introduce a localized hypothermia, for example, to kill off any cancerous cells or that sort of thing, by increasing the density of the swarm. By compressing the swarm together, this will generate heat, which can be used to kill off cancer cells. So how would you go about simulating one of these swarms? Well, as I mentioned at the start, basically what we're considering these to be is just a large number of these small particles. So all we need to do is model one of these particles lots of times, and that will give us our swarm, or a model of our swarm. So a simplistic approach to this is what we, well, not a simplistic approach, a slightly more simplistic approach to this is what we've been using in order to provide a real-time simulation. So the maths that I've been working with is this fairly simple equation down the bottom. All we're doing here is to obtain the acceleration of the particles at a given point, summing together the various forces on them, as can be seen from the free body diagram, and dividing that by the mass. For a more precise result, existing simulators will do more complex calculations than this to provide basically a smoother result over time. But in order to retain a real-time simulation, which was the key goal of this work, what we've done instead is integrated at set time steps to still provide sensible results, but not quite the smooth result, if that makes sense. So yeah, and the free body diagram, I'll just quickly say the main force that users have to control this swarm of nanoparticles is this magnetic force over on the side, and then other forces that play a big role in the simulation would be the drag force, as any movement compared to the fluid flow that the particles are within will provide a drag force which will slow the particles down. You also have things like friction of the particles against any walls, and the forces between particles that help to hold the swarm together. Yeah. So this is a quick video that will just loop in the background. This is what the simulator that's been implemented looks like. It's in real time, so when it loops around again, you'll see this this little needle move up, which is me moving the which is me controlling the swarm in real time. It's written in MATLAB, so that means that we can easily compile this, and this can be run as a MATLAB web application, for example, on Amazon Web Services, which would allow users to use this not necessarily on a high performance computer, but just on whatever laptop they have around, like this little Chromebook that I'm on. It can be controlled through keyboard and mouse input, and I've also connected up an Xbox controller to it, so it's pretty versatile in that sort of sense. And in terms of the numbers of particles, it's very like processing power dependent, but on various computers I can get up to around 70 particles. With a higher performance computer, we'd be getting a higher number of particles than that. So I guess some of the more interesting bits now. I mentioned that I mentioned something about it being simplistic and accuracy and all of that stuff. So how can I say how accurate it is? Well, what we've done is we've verified the simulation against some real world data, some existing real world data. By performing the same experiment in the simulation as had been done in the real world, we can then directly map the data, and it's provided us an 8% average relative error over the 5 points that are mapped here. So what the two graphs are, the first graph on the left over here, this is just the time in seconds on the left for a particle to travel from a starting place to a goal place 1 millimeter along a simulated channel. And on the right hand side, it's just the velocity at the end, which was recorded separately to check that this verified it. And so we're quite happy with an 8% average error. So we then moved on to some parametric studies, just some sort of initial ones to get some good results out of it. Of a few different parameters that we investigated, the fluid flow velocity, so the flow experienced by the particles within the channels, changing that had a very big effect on the number of particles that a user could get from the initial inlet through to a chosen outlet, avoiding the non-chosen outlets. So as you can see, for a lower simulated velocity, the user can get most of the particles to the chosen outlet with a couple of little hiccups and losing 1 or 2 particles maybe. And then from about 0.005 meters per second as the flow in the center of the channel, this then steadily decreases until you get to around this 30% of the particles. So what I don't have in these slides is I ran very quickly in the simulation, setting off the particles and providing no input to them. And for a fluid velocity of 0.01 meters per second, only about 30% of the particles reached the goal. So anything above that 30% for 0.01 would be an improvement on no control over the particles. And so we can assume that all of these values are better results than if we just left it with no user input. I've left this graph in here just to say that there were other parameters that didn't have quite as much of an effect. So this graph shows the capping of the magnetic field gradient, so preventing the user from using the entire simulated power of the coil setup, and how this affected the number of particles that would reach the goal. So obviously, having a lower maximum field gradient, less particles were able to reach the goal over on this side, and then with the maximum 2.25 simulated field gradient, more particles could get there. But as I was saying, this gradient isn't, or this span of results isn't quite as big of a range as I would have thought it could have been. So that was a quick look at the real-time simulator that we've been working on. And in conclusion, we've managed to apply the existing mathematical model used in other non-real-time simulations to a real-time one, while still retaining a level of accuracy of 8% average relative error. The simulator runs in real time, and also through using things like Amazon Web Services, we can have it accessible to various users if they needed it for training or such. And that would be the end of the slideshow.